Welcome, and here's the solution to quiz number 3 for ECE 321. Now, the first problem is looking at filters. Let's see, where's draw? So if I have an input, where in this case, I've got a DC input right here, and then an AC input, find the output when this is fed into your filter. Now, the trick to doing this is to use superposition. I've got basically two separate problems. One's at DC, one's at AC. At DC, the input is 10, the frequency is 0. The gain, this is the gain everywhere. All I care about is the gain at S equals 0 times the input at S equals 0 gives you the output at DC. Repeat for the AC input. For the AC input, x of t is 5. Well, here's x of t. The frequency is 5 radians per second. In phasor form, x is 5 minus j14. The real part's cosine, minus j is sine. Here's the gain everywhere. All I care about is what's the gain at 5 radians per second, times the input at 5 radians per second, gives you a complex number. What that means is the real part's cosine, minus j is sine. So the total answer then is your DC term plus your AC term. Problem 2 is, what's that filter? So this is a 3-stage RC filter. Because R is going up by 10 times each stage, there's almost no loading. So the pole is at 1 over RC. For the first stage, 1 over RC is 71,000. Second stage, 1 over RC is 1667. Third stage, 1 over RC is 116. Plus, this has a DC gain. The gain is 1 plus the ratio. 1 plus R2 over R1 gives you 1 plus 0.5, 1.5. So that's what times 1.5 amplifier. Put it all together, I've got the first pole, second pole, third pole. The numerator, I just made the DC gain 1. And the overall gain is 1.5, so there's your transfer function. Problem 3 looks at a slightly different circuit. This one has positive feedback. What that does is that gives you complex poles. So I've got one real pole at 1 over RC. 1 over RC is 71,000. Over here, 1 over RC is 1667. That's the amplitude of the pole. And the angle comes from here. K is 1 plus the ratio. K is 1.5. That's the DC gain. And that relates to the angle as 3 minus K is 2 cosine of the angle. Solve for the angle, I get 41 degrees. So I've got a complex pole. There's the amplitude, there's the angle, and the DC gain is 1.5. Put it all together, I have the complex pole, I've got the real pole, gives me a third order system. Problem 4 is kind of a design problem. Design a filter that has a gain of 0.9 for frequencies less than 30 radians per second, and no more than 0.2 for frequencies above 50 radians per second. So to do that, if I have a single pole, the gain drops off as 1 over omega. If I have n poles, it drops off as 1 over omega to the n. So as you go from 30 to 50 radians per second with n poles, the gain's got to drop down to 0.2, meaning I need at least 3.1 poles. Round up to an integer, so I could use 4 poles, could use 5 poles. I chose 4. Then pick your favorite type of filter. I chose the Chebyshev filter. From the lecture notes, this is a 4th order Chebyshev filter with a corner at 1 radian per second. Adjust the corner to be between 30 and 50. I chose 30 for Chebyshev filters. The gain's fairly flat out to the corner, then it drops off. So this is probably a good candidate, good starting point. Take this number times 30, that amplitude times 30, and the numerator times 30 to the 4th power. There's G of S. Problem 5 is come up with a MATLAB M file. So I'm going to guess A, B, C, D, E, F. This is what they mean, and this is my target. Calculate the gain versus frequency and return the sum squared error between the two. So if this is G of j omega, that'd be the difference. So here's what an M file would look like. I first need to receive 6 parameters. That's my A, B, C, D, E, F. I need to calculate the ideal gain, that's the red curve. For less than 2 radians per second, the gain is 0.8. Between 2 and 4 radians per second, the gain is 0.2. Between 4 and 7 radians per second, the gain is 0.6. So that gives the red curve. And then interpreting A, B, C, D, E, F, this is what they mean. A times S squared plus B over the rest of it. That'll be your M file. That'll let you try to optimize A, B, C, D, E, F to minimize the sum squared error, trying to come up with a filter that's as close as you can get to the red line, given the constraints that the filter's of this form. Last problem is kind of a tricky one. This is an analog computer. Here's an integrator with 3 inputs. Here's 1, here's 2, here's 3. Here's the second integrator and negative feedback. So what I can do is say this is an integrator. X is the integral, or multiplied by S, minus Sx, since the gain's negative. Minus Sx is 1 over RC times U. 1 over RC is 10. 1 over RC times minus y. That gives 71. And 1 over RC times x. The second integrator, the gain is minus 1 over s times x, or solving for x. Now substitute. That gets rid of all the x's. I have y in terms of u, and solve, and here's what you get. So that is quiz number 3 for ECE 321.